Hello and welcome. In this video, we'll explore optimization techniques for implementing channelized FIR filters using AIEML tiles. Let's dive into how to maximize performance and resource efficiency. These filters are fundamental in many signal processing applications, and optimizing them is key to achieving high throughput and low latency. Let's start with design overview. We'll walk through a real-world design, analyze its compute and I/O demands, and explore techniques to scale it efficiently. We begin by understanding the core concepts behind FIR filtering and channelization. FIR filters are applied across multiple channels, with each channel processing its own data stream independently. This parallelism is key to leveraging AIE DSPs effectively, enabling scalable and efficient signal processing. Let's consider 8-tap channelized FIR filter, a common configuration that balances performance and complexity. FIR filters are applied across multiple channels, and each output is computed by multiplying 8 passed complex input samples, each with 16-bit real and imaginary parts, by corresponding 16-bit integer coefficients, then summing the results. The example design that we have taken for this video targets an AIEML implementation of our FIR filter. The system maintains a 256-bit AXI slave and master interface, ensuring direct compatibility with the existing DSP58-based design. Each channel requires 16 multiply accumulate operations for an 8-tap FIR at 200 megasamples per second. Running the AIEML tile at 1.25 GHz provides 6 clock cycles per sample, meaning the filter must sustain roughly 2.67 max per cycle per channel. Meeting this requirement ensures the AIEML implementation delivers equivalent throughput to the DSP58 reference while simplifying evaluation and integration into customer designs. Each channel requires 16 MAC operations for 8 taps when processing 16-bit complex integer data with 16-bit integer coefficients. AIEML tiles operate at 1.25 GHz and at a sample rate of 200 megasamples per second. Only 6 cycles are available to complete these operations. An optimized implementation uses 16 by 2 element-wise multiplication per MAC operations to process 8 channels in just 4 cycles, leaving headroom for higher sample rates and additional processing. At 200 megasamples per second, 8 channels generate a bandwidth demand of 6,400 megabytes per second. Each PLIO64 interface supports up to 5,000 megabytes per second. So to maintain balanced throughput and avoid bottlenecks, the design requires 2 PLIOs for input and 2 for output. This ensures smooth data flow and supports scalability as channel count or sample rate increases. This architecture uses ping-pong buffers and PLIO64s to manage data flow. Samples are stored locally and processed in 4 cycles. This design keeps compute and I/O in sync, which is crucial for real-time applications. Starting from the left, 2 PLIO64 interfaces bring in 8 samples over 2 clock cycles. Each PLIO64 carries 2 CINT16 samples per clock. Samples are stored in ping-pong buffers within the AIEML tile's local memory. The AIEML tile processes all 8 samples in 4 multiplication per MAC operations. Results are stored back in local memory and sent out via PLIO64s, maintaining pace with input. This design ensures that both compute and I/O are balanced, avoiding bottlenecks and enabling sustained throughput at 200 megasamples per second. Now let's look into design implementation. The design is modular and highly configurable. The header file defines filter parameters including the channel count, which determines how many kernel instances will be created. The kernel contains the core MAC operations, optimized for AI Engine DSP instructions. The kernel source implements the core mathematical operations, multiply and multiply accumulate, on channelized data organized as vectors, enabling efficient parallel processing. Finally, The graph file assembles these kernels into the full design using the 8-channel building block, assigns meaningful names to the PLIO interfaces to reflect their channel data, and applies placement constraints. These location constraints are critical for ensuring consistent performance and predictable timing across all channels. The design approach places strong emphasis on simplicity, adaptability, and defining clear parameters as fundamental principles. Rather than over-engineering, we prioritize clear, maintainable code and well-defined parameters such as sample rate, channel count, and tap length. This strategy is crucial for ensuring the design remains flexible, scalable, and easy to modify to meet evolving system requirements or future enhancements. Optimization starts with a robust 8-channel FIR building block. We apply strict placement constraints to ensure predictable timing and resource usage. Now let's dive into specific kernel and graph level optimization methods that enable us to maximize AI Engine DSP performance. We focus on using only local data memory within the kernel to minimize latency and improve performance. Buffers are carefully assigned to specific memory banks to avoid bank conflicts, which allows us to leverage parallel 256-bit loads efficiently. We reduce stack and heap usage based on compiler feedback, freeing up maximum space for data buffers. Additionally, by using multiple accumulators, we can interleave operations, which helps minimize data movement and keeps the pipeline well utilized. Placement of resources within the AI Engine graph is one of the most important factors for achieving consistent and predictable performance. By strategically positioning kernels and buffers, we can minimize routing delays and ensure efficient data transfer between processing elements. For many designs, the tool's auto-placement capabilities are sufficient. However, when the design involves multiple AI Engine functions or requires complex floor planning, manual placement becomes essential to meet performance targets and avoid congestion. When placing AI Engine kernels, keep these essential tips in mind to optimize performance, reduce routing delays, and ensure efficient resource use. Vertical routing is more efficient, and PLIO interfaces extend beyond the placement area, so aligning kernels vertically reduces routing complexity. Strategically skipping columns aligns vertical routes and PLIOs better within the placement area, which helps reduce latency variation across channels. Limiting the number of rows used in your kernel layout creates space above for additional kernels. This layout maintains vertical routing channels, which simplifies data movement to and from these upper kernels, improving overall system flexibility. Spreading kernels horizontally across the array is possible but less ideal. It can cause latency variations between channels, particularly at the array edges, where horizontal routing becomes congested, impacting predictable performance. Proper placement is essential to maintain consistent bandwidth across all channels. In this implementation, we used auto placement to successfully place 256 channels, and as a result, the throughput remained consistent across all channels, which is critical for real-time, high-performance systems. In summary, AI Engine designs can be tweaked to improve performance, reduce routing delays, and ensure efficient resource use to hit aggressive design specifications. The main design optimizations that can be leveraged are kernel optimizations and strategic placements of AI Engine resources. Thank you for watching.